C depends on P, the force amplitude over stiffness, and then 1 minus beta, 1 minus beta square plus 2 damping ratio beta. There are one new terms in these expressions. Beta. What is beta? Beta is another useful parameter that you have to remember. Beta. Beta is called frequency ratio. Beta is called frequency ratio. The definition is Loading frequency divided by the natural frequency of the system, omega bar over omega n. Be careful about the definition. Beta is divided as the loading frequency over natural frequency. Do not reverse the order, because later on, quite a lot of equation expressed using beta frequency ratio. If you reverse the definition, then it becomes another answer. So please remember this definition: loading frequency over natural frequency, omega bar over omega n. Particular solution: C sine omega bar plus D cosine omega bar t. Homogeneous solution. Homogeneous solution means take force equal to 0, which is equivalent to our free vibration response. UH is our free vibration response. We know UH, we know UP. So now you can put the two things together to form our general solution for our equations. Total displacement. Total displacement is equal to the homogeneous solution, UH, plus the particular solution, UP. This is the general solution for a single degree of freedom system under harmonic excitations. It's quite complicated, right? There are 4 coefficients, A, B, C, D. Some depends on the net damped frequency. Some depends on loading frequency. There are 2 terms to describe their physical meaning. The first part, the blue one, which is the homogeneous solution, we call that transient response. Transient response. Well, the second part, the red one, the particular solution, we call that steady state response. Steady state response. What is transient? What is steady state? Transients, for the blue part, you can see that there is one exponential function. There's one exponential function for the blue plot. Exponential function is a decay function. Decay means as time goes on, maybe go to infinity, this decay function will make this part become 0, right? Just like free vibration. As time goes on, free vibration disappeared. In this equation, if you consider a long time, the blue part will be disappeared. Only the red part remain in these expressions. This is why we have these 2 terms. Steady state means as time goes on, this part will become the governing contribution for our displacement. Transients mean temporary. We have this transient response for a short period of time before all the motion damped down for this part. As time goes on, the contribution for this part starts to decrease and finally drop to 0. Okay. Transients mean temporary, appeared only for a while. Steady state mean they keep forever. As long as your loading remain there. So these are the physical meaning for the response. You can understand mathematically homogeneous particular solution, or you can understand physically. I think it's good to understand both. The transient part, you can see that the transient response depends on the natural frequency, omega n or omega d, disappeared as time goes on because of damping. The second part, the red one, steady state response. This part depends on the exciting frequency, the loading frequency. And this part will be stay here forever, always present. You stay here forever, as long as you are loading right there. Now this page is the derivations, let you know how to evaluate a particular solution. If you like, you may have a look of the derivations here. We take this as our particular solution form, C sine omega bar plus D cosine omega bar, and then we substitute these expressions into the differential equations. Substitute P into the equations and do some simplifications. And then you can do a comparison. The right-hand side, we have a sine function. So the coefficient can map to each other. Cosine terms disappeared. On the right-hand side, there is no cosine terms. So by doing this mapping, you can obtain two equations. Two equations, two unknowns. So you can find out the expression for C and D. If you in math, you can do some grouping or simplifications. Then you can find out the expression for C and D. This is how you can get the expression for CD. For the reference only, not very important. This one is not very important. This page gives you the graphical meaning of our total displacement. This graph shows you two curves. The blue one is the total displacement, with the consideration of UH, homogeneous part, and particular solution. The red one only consider particular solution. From this curve, you can see that at the beginning, because we have two contributions, two components, so the total displacement is relatively big, slightly bigger than the steady state response. But as time goes on, because of damping, the UH component start to disappear. Only the UP remain. So finally, the two curves, they converge to each other. This graph is this picture is a good picture to show you the difference. At the beginning, total different from steady state response. As time goes on, total displacement will finally converge to steady state. Okay, a graphical explanation show you the difference between total and steady state response. If you have time, you can try to substitute ABCD into a software like Excel or the other software. Try to plot the graph yourself. Actually, this graph I plot using some parameters. They give many shapes. When you change the parameter, sometimes you will get another shapes. I would like to mention one term called resonance. What is resonance? Resonance means loading frequency equal to the natural frequency of the system. There are two different things, right? One is loading, one is the structural frequency. But in case if the loading frequency equal to the exciting frequency, mathematically, omega bar equal to omega n. This condition we call that resonance. When resonance occurs, the displacement normally becomes very, very large. But from this graph, you can see that the displacement needs to take some time to evolve. At the beginning, the displacement is still small, but you can see that the displacement will increase gradually, and then finally becomes a very, very big number. Later on, I will show you how to get the numbers. But here I show you the graphical meaning first. Resonance. When loading frequency equal to exciting frequency, we understand that this is so-called resonance, a very special phenomenon. The structural response becomes very, very large. The displacement of the building becomes very, very large if loading frequency equal to natural frequency. But this picture just want to let you know that actually they have to take some time for the displacement to evolve. The displacement will not suddenly jump to very, very large. It needs some time to evolve. This equation is not very important, just copy from the book. let you know the expressions. This one is important. Steady state response is important. Okay, steady state response is important. Steady state response means the particular solution, UP. This one is important. Steady state response. This one is important. Solution is two parts. And particular solution. But as I mentioned before, the homogeneous solution will finally disappear in the structures, in the problem. So normally we will consider the steady state response only, because the first term will disappear as time goes on. They only affect for a short period of time, not permanent. So for our analysis, we commonly ignore the homogeneous response. I turn this to gray. Not important, this part. We just consider particular solution, a long terms here, long expressions. But some guy, they do some simplification for this particular solution. They rearrange this complex form, sine, cosine, with large coefficients. Some guys simplify these expressions to a more simplified version, more simple versions. U, I ignore homogeneous solution. U is equal to UST times RD times a sinusoidal function. Similarly, we can group sine, cosine into one single trigonometry function. Here we use sine. Here we use sine. After this grouping, there were some changes in the coefficients before the sine function. And there is one more angle inside the sine function. What are their meanings? UST, this term, it is equal to P over K. UST0 equal to P over K. P is the force amplitude. P0 is the force amplitude. K is the stiffness. The force amplitude over stiffness, actually the first coefficients of the original form. Why we call this static? Why we call this ST? ST means static. Why we call this static? Because this term, it seems that this term is something like a constant. P is a constant, right? K is a constant. The ratio gives you something like a constant, a static. So here we normally call this static displacement, UST, force over stiffness. The second terms, RD. RD, we call that dynamic magnification factor, DMF. Dynamic magnification factor, DMF. It describes the dynamic effect of a system. This term represents the dynamic effect of the system. It is calculated using these blue equations. Dynamic magnification factor depends on two parameters, beta and damping ratio. Beta is frequency ratio. Damping ratio is the thing that we mentioned in free vibrations. If you know beta, if you know damping ratio, then you can evaluate this dynamic magnification factor. Okay, it's talk about the dynamic effect of a system. The last one is phase angle. Phase angle appeared inside the sine function. I will explain the meaning of them using two simple examples. But you can take a look on the equations. We ignore the homogeneous solution, just consider the steady state response. And then by doing some grouping, we can simplify our problems into this form. Displacement will follow this pattern to oscillate. And the coefficient before the sine function describe the radiation amplitude. The coefficient before the psi function describes the radiation amplitude at steady state. Right? Because psi is bounded by 1 and minus 1. So the maximum displacement is governed by UST times RD. You can call this displacement amplitude U0. Normally we put a subscript 0 to denote the maximum number, the amplitude. Okay. The displacement amplitude at steady state is equal to UST times the dynamic magnification factor mathematically. It's quite interesting because when you take a look on these expressions, for a dynamic system, the radiation amplitude is equal to the static terms, this part, P over K, is equal to a static part multiplied by a factor, RD. A static response amplified by a magnification factor, RD, gives you the dynamic radiation amplitude. So as I mentioned in the descriptions, RD is just like a factor to account of the dynamic effect. It will amplify the static displacement by n times bigger than the static radius due to dynamic effect. This factor can be calculated using beta, using damping ratio. UST is called static deformations. UST. Calculate based on P, based on K. There are two constants for given problems. Well, I used two examples to discuss what is dynamic magnification factor and the phase angle. When we just take a look on the previous equation, maybe it's quite difficult to understand the physical meaning. So here I use two simple examples to illustrate what is dynamic magnification factor and also the phase angle. Static. Well, static problem. Be familiar with this static. When we have a spring mass system under a constant force, P0, the displacement is equal to UST. If you know the spring constant, then you can easily find out the expressions of UST, which is equal to P over K. That's why we call that UST. P over constant K give you the static deformations. For our dynamic problems, if the force is a dynamic loading, the amplitude is also equal to P0. But this time the force is not a static force. The force is a sinusoidal force, oscillating with a loading frequency, omega bar. When you change the force to a sinusoidal force with the same force magnitude, then what will happen for our displacement? Based on our previous discussion, the dynamic displacement at steady state is equal to this equation. U0 is equal to UST times RD according to our previous formula. So you can see that for a dynamic system under a sinusoidal force, the force has the same amplitude. We observed that the displacement for a dynamic system is now equal to the static part. The static part is from our static problem multiplied by a modification factor, RD. RD is called magnification factor, dynamic magnification factor. It seems that dynamic response, when the force starts to oscillate, it will change our displacement using this factor RD. It may be bigger, it may be smaller, depends on the value of RD. If RD, say for example, if RD is equal to 2, then you can see that dynamic displacement will be 2 times bigger than the static part. If RD is equal to 3, then the dynamic displacement will be 3 times bigger than the static value. So that's why when you consider dynamic force, sometimes the dynamic force can make the result n times bigger than the static values. Okay, you may have this kind of mindset. When you talk about dynamic, sometimes the displacement, the response may be n times bigger. Depends on the values of RD. Now, but there's another scenario. RD is not always bigger than 1. Sometimes RD is less than 1. Sometimes RD is less than 1. Depends on what? Depends on this equation. You can calculate RD using this equation. Depends on what number you have. Some combination make RD becomes magnification factor. Some combination make RD becomes less than 1. Reduction factor. Now here. So this example just want to discuss a little bit about the meaning of RD. RD just like a magnification factor modified a static response to a dynamic response. Okay, these are some discussion about dynamic magnification factor. Another remarks is that when you read some textbook call RD as another terms called displacement response factor. Some textbook call this dynamic magnification factor. Some call this deformation response factor. They are just some terminology. The meanings remain the same. The meaning remains the same. It's just like the ratio between the dynamic response amplitude to static one. Or you can calculate using frequency ratio and damping ratio. Okay, this example will let you know what is RD, dynamic magnification factor. And what about the other number? There is a phase angle inside the sine function. What is the impact of the phase angle? On the next slide, page 13, I use another simple example to illustrate what is the so-called phase angle, phase lag, which is calculated using this formula. Phase angle. Suppose we have a spring mass system again under a sinusoidal force. The force, the loading is a sine force, oscillating with frequency omega bar. The displacement of the corresponding system. We know the expressions and give you the formula. Displacement, also a sine function, but there is one phase angle phi inside the sine function. What is the effect of phase angle? To make things simple, I just assume that phase angle equal to 90 degrees. Actually, you have to calculate yourself based on damping ratio, based on frequency ratio. But to make things simple, I directly substitute a number for phi to have look what happened of phi. And you can see from this graph, at time equal to t1, the force reach its maximum level, but the displacement is not maximum. Displacement is not maximum. After a certain period of time, right here, at time equal to t2, force drop to 0, displacement reach its maximum level. So what we observe, what we observe right here. Firstly, we observe that displacement maximum and force maximum, they are not occurred at the same time instant. Maximum force doesn't mean you get maximum displacement. There are some time lag. There are some time lag behind. Maximum force occurred at time equal to t1, and then after a certain time at t2, displacement reach its maximum level. They are not occurred simultaneously. Okay, they occurred at different time instants. And that's why we call that phase lag. The displacement response will be appeared later or earlier, depends on the value of the angle. Okay, they are not occurred simultaneously. There are some time lag between the force and displacement. This is another interesting observations for a dynamic system. In the past, for static, we think that maximum force equals maximum displacement. They appear together. But for dynamic, you can see that no, they may occur at different time instants. This is another thing I want to share with you about phase angle. So in our formula here, for our general solution, at steady state. This one. This equation is important. For this equation, now you know the meanings of RD, you know the meanings of phase angle. Okay, you know how they affect our dynamic system. One affect the amplitude, one affect the time when they reach their maximum number. There are two new terms for a system under harmonic vibrations. Okay. After some illustrations, let us go back to the equations. RD, we call it dynamic magnification factor. It can be calculated using these equations. Depends on beta, depends on damping ratio. On the right-hand side, I plot a graph to describe the relationship between RD to frequency ratio, beta. This graph is very, very useful to let you understand the response of a single degree of freedom system under harmonic loading. How? I use the blue line as example. Blue line is plotted using damping ratio equal to 5%. I put damping ratio equal to 5% into this equation, and then I use Excel to try different value of beta, and then find out the corresponding value of RD and plot it on the graph. So I get the blue line. You can redo the things using different damping ratio. What we observe from this graph, why I mentioned that this graph is very useful, because it helps you to understand the dynamic behavior of a system. Let us have a look from the left to the right. Here, we start from here. When beta equal to 0, what is the meaning of beta equal to 0? Beta means frequency ratio. By definition, it is equal to omega bar over omega n. Beta equal to 0 means the denominator equal to 0. Right. What is the meaning of loading frequency equal to 0? Loading frequency equal to 0 means the loading does not oscillate. It is a constant force. It is a static force. Okay? When beta equal to 0, actually it means static. The force doesn't move. The force is a constant. In these situations, when beta equal to 0, RD is equal to 1. When you go back to this formula, RD equal to 1 tells you what? Tells you the dynamic response equal to the static response. It makes sense because we are talking about static at beta equal to 0. So actually, the first point is talking about static. In the past, our static situation is actually just one point among all frequency domain. Okay, static is one very special situation at the beginning of this graph. Okay, and then when beta increase gradually, up here, when beta increase gradually from 0 to 0.3, the loading start to become a dynamic force, start to oscillate. Then what we observe? We observe that when beta increase, the value of RD increase from 1 to 2, 2 to 3, 3 to 4, depends on the on the coordinate you consider. And then at beta approximately equal to 1, at beta approximately equal to 1, there is a big value for RD. Can't see from this picture, but there is a big number right here. It means that the dynamic response becomes n times bigger than the static response. We call this resonance, right? Resonance when beta equal to 1. When beta equal to 1, which means the loading frequency equal to the exciting frequency, we call that resonance. Did I mention terms? Anyway, let's continue. Beyond this resonant frequency, when the loading frequency increase further, well, we observe that the RD value start to decrease. When beta increase further beyond this level, beyond this point, beyond this level, we observe that RD becomes a value less than 1. Becomes a value lesser than 1. Lesser than 1 means the dynamic behavior start to make the response smaller than static. Okay, smaller than static. So dynamic is not always amplify the loading. Sometimes they will make the displacement smaller. Depends on beta, depends on damping ratio. There are combinations. This graph actually shows you how the system change when loading frequency change. That's why I think it's quite useful to understand the impact of loading frequency to the system. Sometimes big, sometimes small. Then what about damping ratio? Damping ratio. I use different color on this graph. There is one consistent arrangement, consistent change for damping ratio. When damping ratio increase from 5% to 10%, from the blue to the red line, you can see that the whole values decrease. Similarly, when damping ratio increase from 0.1 to 0.7, from the red to the green line, all the values of ROD decrease among all frequency range. It makes sense. The higher the damping ratio, the lower the maximum response. It makes sense. But the shape of the graph also changed significantly. For small damping, you appear a peak. There are peak at resonance. But for high damping beyond 0.7, you cannot see that peak. Beyond 0.7 damping, there's no seems that there's no peak values. There's no that jump. You may plot this graph yourself using Excel by changing damping ratio and frequency ratio. The expression on the left just showed you some scenario. When beta very small, then RD equal to 1, which means the static scenario I just mentioned. When beta approximately equal to 1, resonance, you have a big number at beta equal to 1. When beta bigger than 1, RD is approximately equal to 0. So that means here, there are 3 extreme points. At the beginning, at resonance and a large loading frequency. When beta is close to 1, we call that resonance. When beta approximately equal to 1, we call that resonance. At resonance, the structural response becomes very big. So if possible, try to avoid this happen to your structures under considerations, because at resonance, the displacement can be n times bigger. Just like here, when damping ratio is equal to 10%, at resonance, the dynamic response will be 5 times bigger. You can calculate RD at resonance using this formula. 1/2 times damping ratio. Actually, it just derived from the definition. You put beta equal to 1. The first term cancel. Beta 1. And then you can see that square root to damping ratio square. The square cancel. Only 1/2 damping ratio remain on the right hand side. Actually derived from the definitions. And this graph shows you the effect if you have different frequency ratio graphically along the time domain. This time, the horizontal axis is time, not frequency. You can also understand the effect along the time domain, along the time series. The y-axis. The y-axis is the displacement, normalized by the static displacement. We normalize our displacement by the static value. So that it's more easy to compare. For comparison, the first graph showed mu beta equal to 0.5, frequency ratio equal to 0.5. The second picture B showed mu at resonance. The last picture showed mu beta equal to 2. You can see the difference. There are some observations, right? The dashed line represents static, while the solid line represents dynamic. Static, dynamic, they are not occur simultaneously because we have phase angle. And when beta equal to 0.5, according to the previous graph, when beta equal to 0.5, there will be some amplification factor here. RD is bigger than 1. So you start to see amplification effect. The dynamic response will be here is 1.29 times bigger than static. At resonance, beta RD is equal to 2.5. The dynamic response is 2.5 times bigger than static. And they occur, the maximum displacement occurred later than the static values. The last picture C, when we have large damping, when we have large frequency ratio, we see that there is reduction factor. RD is equal to 0.32. Reduction factor. The dynamic response is even smaller than static. And when you have maximum value in our static part, the dynamic will become negative. That means they occur something like our phase. We call it our phase. When the loading on the right and the displacement on the left, they are our phase. These three graphs just let you know how they change along the timeline. The previous picture let you know the frequency, how the frequency change to affect the system. Here show the time, how they evolve. Okay, maybe we can take another short break for 5 minutes. Okay, testing. Welcome back. Before the break, we start to introduce a new chapter, topic 6, force derivations. There are different forces acting on the structures. This can be a psi force, cosine force, impulse loading, or the other situations. There are many different forms of forces we will consider in this chapter. But normally, we use psi at the beginning, let you know how to deal with a psi force. In the future, you will also learn how to deal with impulsive loading or the other thing else. Before the break, we mentioned what? Before the break, we mentioned a useful equation here, on page 11. We discussed several items, but I think this one is important. Steady state response. We normally use this equation to evaluate the response of a system under a sinusoidal force. So please make sure that you remember or you understand this equation. Steady state response for a system under sinusoidal force. And then we discuss some physical meaning right here. We start from this page, page 16. We know the steady state response of a system. Among all frequency, there is one special frequency we are very rare of, which is the resonant frequency. Resonant frequency means beta equal to 1, or loading frequency equal to the natural frequency of the structures. For this case, when you substitute beta into our formula, you can find that RD is equal to 1/2 times damping ratio. And then among all frequency range, this value is the maximum number, maximum RD at resonance. About the phase angle, you can also calculate phase angle, but phase angle normally is not our interest. For our engineering practice, we would like to know the maximum displacement, the maximum value, not the time. When they achieve the maximum value, it's not our interest. We just want to know the maximum displacement, and then compare with our diffraction limit or the other thing else to see whether failure or not. The time is not normally not our interest. But at resonance, phase angle is 90 degrees for the informations. That means the response is left behind the loading by pi/2 radian. At steady state, the displacement can be revised into this format. RD is equal to 1/2 times damping ratio. Phi is equal to 90 degrees, or you may use radian if you like. The displacement amplitude is equal to the constant part P of k times 1/2 damping ratio. These are some equation that you may use at resonance. Or maybe you can use the general one, the one that I showed you before. Put beta equal to 1. One very simple applications. Example 1. Assume that we have a single degree of freedom system. I give you all the mass, stiffness, damping ratio. Suppose this system is under a sinusoidal force. The force amplitude is 1000 kilonewton. It is a sinusoidal force. In this problem, we would like to determine the steady state response for loading frequency equal to 2 times natural frequency. Second, loading frequency equal to 0.5 times natural frequency of the system. The last one, resonance, loading frequency equal to natural frequency. We try different frequency ratios, simply speaking, to see the effect on our steady state response. It is a direct application of the formula that we derived before. Steady state solution. When we deal with a single degree of freedom system under harmonic force, we normally use our steady state solution to determine the structural response. Displacement is equal to this equation at steady state. UST time RD time an oscillating function psi something. On the top right-hand corner, I also calculate the natural frequency of a system. Square root K over M. You know K, you know M, so you can evaluate natural frequency immediately. K and M are given in the problems. This question, I give you the dynamic properties. The more we have to do, we just calculate what is UST, what is RD, pretty straightforward. And also fine. Beta. The steady state solution depends on frequency ratio beta. Beta is defined as the loading frequency over the natural frequency of the system. Loading over the natural frequency. Remember this pattern. Loading frequency at the top, natural frequency at the bottom. According to the question, part one, we assume that loading frequency is 2 times natural frequency. So just simply speaking, beta equal to 2. When beta equal to 2, you can put it into the equation of RD. RD is equal to 1 over square root 1 minus beta squared, the whole thing squared, plus 2 damping ratio beta squared. Use this equation carefully, then you can find out RD, which is equal to 0.333. 0.333. For high frequency, it seems that RD becomes a value less than 1. It shows us some reduction effect. UST, the static component is equal to P over K. P is the force amplitude, 1000 kilonewton, according to the question. K is also given in the questions. So the ratio gives you 0.01 static. You know the dynamic magnification factor, 0.333. So the plot of them gives you the displacement amplitude for this dynamic system, lesser than the static one, because of high frequency. Higher frequency seems that it will tend to reduce the displacement amplitude. I also calculate the phase angle for reference. Displacement amplitude equal to UST times RD, 0.0035 meters or 3.5 millimeters. This is the displacement amplitude at steady state for our system when beta equal to 2. If you like, you may compare with the diffraction limit, right? For beam design, you have beam diffraction limit. For structural design, you have structural displacement limit. You can compare with the amplitude with the diffraction limit to see if there's any problems. Case 2. For case 2, loaded frequency is equal to 0.5 times the natural frequency of the system. I just change beta to 0.5 and redo the calculation once more time. Static remain unchanged. UST remain unchanged because it depends on the same two numbers. RD, when beta changes to 0.5, RD becomes 1.333. This time, RD is greater than 1. Greater than 1 means it seems to have some magnification effect, amplify the static response by 1.33 times. The dynamic response is now bigger than the static one. 14 millimeters right here. The last one, at resonance. At resonance, beta equal to 1. At resonance, we redo all the things again. UST equal to 0.01 meters, which is equal to 10 mm. RD, wow, we have a big number. RD is equal to 25. 25 means there is a big amplification effect. the vibration amplitude is now equal to the static one times RD. RD is equal to 25. So the displacement dropped to 260 millimeter. When you consider a static, 10 mm, dynamic, 200 something. So you can see that if your design ignore the dynamic effect, sometimes you may see a big difference in terms of your analysis results. In this example, we have a big amplification effect at resonance. Because we have small damping, our damping ratio is 2%, right? Our damping ratio is 2%, so we have a large amplification factor at resonance. The higher the damping, the lower the amplification factor, as we discussed before using a graph. Yeah, I just want to let you know that for a dynamic system, the response is not only depends on the force amplitude. In this question, the force amplitude remains the same, 1000. But you can see that if you change the frequency ratio, if you change the loading ratio, the loading frequency, or the frequency ratio, the response amplitude also change. Here, show you another formula. Elastic force. Elastic force means the force due to the stiffness component. Stiffness components mean the column. The column provides stiffness. You can evaluate the force applied on the stiffness component, applied on columns or the beams, using this stiffness formula. We learned this in topic 4, right? Elastic force equal to stiffness times displacement. Now you know displacement. Displacement obtained under sinusoidal force at steady state. If you know displacement, displacement times stiffness give you force, elastic force. Tells you more. This is one trick we normally do for a dynamic system. For a dynamic system, we calculate the response depends on the loading. At this stage, you know how to solve for two scenarios. Force equal to 0 or force equal to a psi function. You know how to deal with these two scenarios right now. Anyway, given the force, you can determine the displacement function u. At each time instant, at time t, from the displacement function, you can evaluate the displacement at any time. Say, for example, the first second, the first second, or 1 hour later, right? Depends on the time you want to consider. At any time instant, the force, the elastic force applied on column is equal to stiffness times displacement. Okay, Hopf slope. The force, elastic force provided by the structures is equal to the stiffness of the whole system times the corresponding displacement at that time. So here the idea is that we can convert displacement back to forces. Why we are doing so? Because in your structural design, you normally deal with force, right? You want to know the moment diagram, shear force diagram, etc. But up to now, I just mentioned how to calculate displacement. This slide shows you the idea how you can use the displacement response, the displacement results, to calculate the forces applied on the structures. Right, just like here. Firstly, you solve a dynamic problem, find out the displacement history, and then depends on what time you're going to consider. Normally, you consider the time that gives you maximum displacement. Right? Maximum displacement gives you maximum force. The force at time instant t equal to K times the corresponding displacement. This force is so-called the equivalent static force. And just like that, there is a static force applied on the structures right here. The force magnitude is equal to K times displacement. At this stage, you can treat this as something like a static system. Okay, you can treat this as something like a static system. You can conduct static analysis to find out the column force or the beam force. You can use equilibrium. You can use force equilibrium to find out the column force or the beam force, if there's any. That's why we call it equivalent static system. Not exactly static, but for analysis purpose, you can treat this as something like static to evaluate the column force, column shear, or column moment. If you know the column force, then you can design the column. Okay, this is what we normally do for dynamic analysis. We firstly solve for displacement, considering pure dynamic problems, and then once you know the displacement, you can freeze the structures at different time instant. You can freeze the structure, pause the structure, stop it, okay, just like static. Based on the displacement, you can convert this back to force, and then right now you can conduct analysis to find out the column force or the beam force. That's why we discuss how to find out displacement, because it helps us to find out the column force or the beam force for analysis purpose, for design purpose. One remarks. In these sections, we discuss how to deal with our problems under a sinusoidal force, structures under a force applied at the mass level. And other situations is for structures under a ground motion, a ground excitations. For ground excitations, if the ground excitation is a very nice function, if the ground excitations also follow a sine function like this, mu double dot g is the ground acceleration if the acceleration of the ground can be modeled using a sine function. This becomes the equation of motion. You can group the coefficient into a single number. Okay, so actually you can see that these are two identical problems: are structures under a sinusoidal force and are structures under a sinusoidal ground acceleration. You can see that actually they are the same problems mathematically. So if I ask you the problem, hey, we have a structures under a sine ground acceleration. I ask you, hey, what is the displacement? I think you should be able to answer these questions, right? Because they have the same formula, same outcome. Now, this is true if the function is a sine here. If you consider earthquake for sure is not a sine function. So if the ground motion is an earthquake, something like a random motion, then you need to use a more advanced technique to find out displacement. But at least for sine function, we have some analytical solution. So now we know how a structure oscillates under a sinusoidal force. In theory, for our structures under cosine force, they look in the same manner. We also know how to find out the displacement response at steady state. We discussed the effect of frequency, discussed the effect of damping ratio, etc. The more next, there are some applications for harmonic vibrations. There are a few applications. Last time in topic 5, free vibrations. Free vibrations will have one application related to damping calculation, right? Calculate the structure, calculate dynamic property in free vibrations. What about harmonic excitations? There are several applications right here, more than free vibrations. In this session, session 2, we will discuss a few examples how we can apply our results to daily applications. There are totally 4 applications that we will go through using the concept of harmonic excitations. The first one is harmonic vibration generator. The second one is measure damping ratios. The third one is force transmissions. The last one is vibration measuring instruments. There are 4 applications. The first one is I put a 1 here on the top right-hand corner, let you know where we are. Application 1 is talking about how to generate a harmonic force of a structures. For analysis, it's quite easy, right? For our structure analysis, you can just say, hey, we have a force applied on top of structures. For our calculation, you can always assign loading easily. But in reality, in a real building, how to apply loading on the structures is not easy, right? This page shows you some idea. Actually, you can use something like vibration generator, something like a machine, to generate harmonic force, a sine force or cosine force. How? One model is like this. This machine has a support. There are 2 mass, one on the left, one on the right. These 2 mass, they will rotate in opposite directions. When the mass rotate, they require to have one centripetal force for circular motion. For a mass under circular motion, there must be a force pointing towards the center for circular motion that you learned in physics. When you take a look on this graph, they are diagonal, pointing towards the support at the middle. You can find out one component, one downward component, and horizontal component for each mass. Similarly, for the mass on the right, you can find out the vertical and horizontal component. When you take a look on this picture, you can see that the horizontal component cancel out each other. Only the vertical component remains. The vertical components follow something like a sine function. So this is one way to generate a sinusoidal force. This is the force amplitude, P, times sine omega bar t. When these 2 masses rotate, it will generate a harmonic force. The loading frequency depends on the frequency for the mass to rotate. The higher the rotation speed, the higher the frequency. This is how you can generate force at different story level. With these structures, you can put this generator on the platform on the force slab, and it would generate a sinusoidal force horizontally on the structures. Just for the information, this one is not very important. Another one, more important applications. How to measure damping ratio again. In topic 5, free vibrations, I mentioned that you can use free vibration to measure damping ratio. Actually, for harmonic excitations, you can also use the outcome in this chapter, topic 6, to evaluate damping ratio. You have more than one way to evaluate damping ratio. You can use free vibration response, or you may use harmonic vibration response under sine force or cosine force. You have more than one way to evaluate damping ratio. In this section, we will introduce 2 methods based on harmonic vibration response. The first one, method 1. We call that resonance amplification method. How to do so? Suppose you have a structures. Suppose you have a structures. You want to evaluate the damping ratio of these structures. Then what to do? Firstly, you try your best to excite the structures to undergo harmonic vibration using a sinusoidal force. How to apply sinusoidal force? Maybe you can use the vibration generator that I discussed on the previous slide. You try to excite the structures to undergo using this sinusoidal force. You need to change you have to change the loading frequency gradually. At the beginning, you apply static force. That means frequency equal to 0. You apply a static force on the structures, and then you record the corresponding displacement of the system. The maximum displacement for sure. And then you change the loading frequency. You change the loading frequency from 0 to maybe 10 or the other numbers. Change it to another loading frequency. And then when the structure oscillates, you record the displacement history and then find out the maximum value. Then you can plot another point on the graph. So you can see that when you apply different loading frequency, different forcing frequency, you can hopefully plot a curve like this. For high frequency, the response will be smaller and smaller. By applying different loading frequency, you can sketch the response at different frequency number. This response is called frequency response plot. Okay, this is how you can get this curve. Actually, it comes from different tests. You have to change the forcing frequency gradually in order to draw this line. So what to do? Well, assume that you have this curve. Assume that you have already get this frequency response plot. In this graph, we need two coordinates. We need 2 points. The first one is here, static. The second one, at resonance, the peak number. At resonance, we need these 2 coordinates, these 2 points. According to our discussion, harmonic vibration response at steady state. Dynamic magnification factor at resonance is equal to 1/2 damping ratio. This is the equation we discussed at resonance. At resonance, beta equal to 1. Dynamic amplification factor, RD, is equal to 1/2 times damping ratio. At the same time, by definition, RD is equal to the maximum dynamic response at resonance over static displacement. This is by definition. By definition, U maximum response over static gives you the factor RD. So from these equations, from the graph, you can find out U0, you can find out UST. You can take the ratio to find out RD obtained from the graph. And then by a little calculation, you can find out damping ratio. Okay, this method is called resonance amplification method. This method is called resonance amplification method. Using the result at resonance and at static to evaluate damping ratio. You require 2 points. 2 points. Okay. The other method, method 2. Method 2. Method 2 is that we call the half power bandwidth method. Method 2, we also need to get this frequency response plot. Suppose you have conduct the lab to get this frequency response plot. Half power bandwidth method rely on only 1 point at resonance. This method, half power bandwidth method, only need 1 coordinate, at resonance, the peak number at resonance. Assume that the value here is equal to U0, the peak number. And then there's one very special step. We calculate a number, a magic number, u0 divided by square root 2. We calculate a number at this level, u0 over square root 2, and then draw a line at this level. This line will cut through the curve by 2 points. 2 points. From the curve, you can find out the frequency correspond to these 2 points. I call this FA and FB. Okay? Some engineers prove that damping ratio can be calculated using these two special frequencies, FA and FB. You can also use frequency ratio, but here we use FA, FB. This is half power bandwidth method. Firstly, find out the response at resonance, and then calculate a magic number, u0 over square root 2. This magic number will cut through the curve at 2 points. Find out the frequencies corresponding to these 2 points, and then use the half power bandwidth equation. It will give you the damping ratio. The advantages of this method is that you don't need to know what happened at static. You don't need to know what happened at static. If you use the previous method, resonance amplification method, this one, if you use this method, resonance amplification method, you need 2 points at resonance at static. When you use half power bandwidth method, you only need one point. You need fewer informations. Actually, it's quite difficult. It's quite difficult to get static response for structures, for a real building, because how to apply static force on the structures? It's not easy, right? For a building, you have no support on the surrounding. It's quite difficult for you to apply static force on the structures. But what about dynamic force? For dynamic force, you may use something like vibration generator. You can put the machine on the platform. When this machine operates, it will generate a dynamic force. But this method does not apply for static. So these are two methods, two extra methods for you to evaluate damping ratio. So in total, you know totally 3 methods to evaluate damping ratio. 1, using free vibration response. 2 more methods using harmonic vibration or sine force, cosine force, these kind of things. You learn totally 3 methods to evaluate damping ratios. So at least you have some more idea how to evaluate this magic number. The next slides, page 28, show you a short derivations. Why half power bandwidth method have such a magic number? If you like, you may have a look at these derivations. It's let you know why we consider a magic number square root 2. One short example to let you know how to use resonance amplification method and half power bandwidth method. Suppose we conduct many tests on a building, and then we can get this frequency response plot as shown on the picture at the bottom. The dot represents the frequency under considerations. We consider frequency 16 Hz, 70 Hz, 18 Hz, and then so on to get this graph. Evaluate damping ratio using both methods. How? 2 methods. Method 1. Suppose I use resonance amplification method first. How to use resonance amplification method? Once you do that, you need to obtain 2 coordinates, 2 points from the graph, right? You need to know, you have to know the response at the peak level at resonance. From the graph, you can see the peak response easily at resonance. This number, 567 times 10 with exponent -2 inch. If you use resonance amplification method, you also need to know what happened at static. You have to know what happened at static. But however, from the graph, it does not show what happened at frequency equal to 0. You don't know what is frequency equal to 0 from the graph. The more you can do, if you really need to use this method, if you really want to use resonance amplification method, then you have to try your best to estimate what happened at frequency equal to 0. Maybe you can use extrapolate, you extend the line to 0, something like that. Not very accurate, but this is the only way that you can get static. You can extend this line to level 0 to see what happened. But you can see that the scale of this picture is not precise right here. 16 and then 0. Actually, this is not very accurate if you do this extrapolate. But in case if you really want to use resonance amplification method, then you have no choice because you need two coordinates. One at the peak, second at static. Here I assume that after extrapolate, I will get a number 0.5, just guessing, Not very exact. So according to the resonance amplification method, U over UST equal to 1 over 2 damping ratio. You know maximum response, you know UST. So by doing this simple calculation, you can get damping ratio, 4.4%. But you can put a question mark here. Because there should be some problem about this static response because we just roughly estimate using extrapolations. Suppose the error should be big, right? Not small. But anyway, 4.4% using this method. Method two, half power bandwidth method. Half power bandwidth method rely on only one point at the peak level. Here, at the peak level. At the peak level, the value is 5.67 over 100 inch. If you use half power bandwidth method, we have to calculate one magic number, U0 over square root 2. You can use your calculator, calculate U0 over square root 2, and then draw a line. The line will cut through the curves at 2 points, here and here. You try to do a mapping, find out the corresponding frequency, correspond to these 2 points. From the picture, frequency 1 is 19 something, frequency 2 is 20.42. And then you can use the half power bandwidth equation. F2 minus F1 over F1 plus F2. And this one you can see that damping ratio is equal to 2.18%. There's no need to get the beginning point, no need to get the static one. So if you ask me, I think method 2 is more accurate in this example, okay? Because you don't need to make any assumption at the beginning point. But method 1, I just for illustration, I let you know how to use it. Although I think the accuracy is not very good, right? Around double. Okay, I think I don't have time to complete the remaining sections. The discussion for the third application is also quite lengthy as a lorometer. I think I don't have time to complete the remaining sections. Let us continue next time, okay? Is there any questions regarding to the natural materials so far? Although we mentioned something about forced vibrations, Here, Foster vibrations. We use harmonic vibration to start our discussions. Normally, we do in this way in all the dynamic textbook. We discuss the problems. I think the most important thing is in terms of calculation, we normally use steady state response. Steady state response. In our discussions, we mentioned that the true solution composed of two parts, transient part and steady state response. But the transient part will disappear as time goes on. That's why in practice, we normally play with the steady state response, the red part here. The red part can be simplified to this version, UST, RD, and psi. It's more easy to apply. So you have to remember this equation. And then in this note, I use a few examples to illustrate what is RD, what is phase angle, let you understand more. And then we discuss a few applications, vibration generator, damping ratios, calculations. Next time, we will discuss the remaining two. And then hopefully we can discuss another type of loadings, impulsive loading, right here, impulse loading. Impulse loading. Next time. So let's see if we have any problems. If no, maybe I finish the lecture slightly earlier. If you have questions, you may stay here. If you have already finished your assignment, you may upload your assignment to Moodle. Otherwise, you still have one more day. You can, at the deadline, I postponed it to tomorrow. If you have not yet finished, at least you have some time to work on. If you have already finished, you can directly upload your answer to Moodle. Then you may have a rest on during the weekend.有冇問題？哎呀！如果冇問題咧，咁你哋可以去食個飯啦。你哋下晝應該仲有第二堂嘅，係啦。如果有問題嘅，咁你可以 stay 喺度啦。我哋仲有少時間嘅。好，拜拜啦，下回 OK，下星期再見啦。